Hi class. Sorry I couldn't be there today. I know that you are absolutely devastated, but hopefully this video lecture will help. And I must extend my sincerest apologies to your guest teacher, especially by the time you get to sixth period. This will be the third time she's seen it, so be nice. It's probably been a rough day. With that said, let's look at electrons in atoms. So 2 days ago we looked at light and light waves, different kinds of electromagnetic spectrums. Now we're going to look on a subatomic level and look at the electrons. So there were several different atomic models that have been gone through over the years. One of the first was Thomson's model, and he thought it was kind of like a blueberry muffin. So you had a big sphere of positive charge, something like, the batter of the muffin, and then a bunch of electrons kind of studded throughout, which would be representative of the blueberries. So on your paper, you actually have 4 little circles. One of them you can fill in a diagram looking like this and label it the plum pudding model. I'll give you a minute to do that. Alright, since I'm not there, I don't know if that was enough time for you, but good news is this lecture will be on YouTube for you to reference if you don't get everything today. So the Rutherford model, he proposed that most of the atom's mass was found in a positively charged middle, and this is what he did with his famous gold foil experiment. So essentially he took a piece of really, really thin gold foil, he shot alpha particles at it, and then he had kind of a background to catch the alpha particles to show where they're hitting. Most of the time the alpha particles went straight through, so that would be representative of them going through where there's no mass really. However, every so often he would get one that would be deflected in a direction other than the direction that he was shooting the beam. And that led him to propose that it must be hitting something of the same charge and it's being deflected. And that's how he came up with the fact that there's a dense positive center and a negative cloud kind of around the outside, or a negative area. So you could draw this in the second circle, a positive center and a negative outer ring. I'll give you a minute to do that. Alright, moving on. We have the Bohr model, and he proposed that electrons traveled around the nucleus in definite orbitals. So this would be akin to the planets kind of going around the sun in our solar system. They followed a definite path, they were locked in there, they're very discrete in their locations, you always knew where they were. So this would be the third circle that you have in your margin that you could draw. It would be the Bohr model. I'm just going to imagine you all diligently filling in the models. Alright, the next one we have is the quantum mechanical model. This model believed that it had no definite shape and they didn't have precise orbits. So they kind of envision them just zipping around the nucleus in whatever fashion they want. And this is what we're going to fill in our fourth circle that you have. And here a little bit more about Niels Bohr. He was a student of Rutherford, and he proposed that electrons traveled in concentric circles around the nucleus. So that would be like the planetary motion. Um, he proposed energy levels so that the region around the nucleus where the electron was likely to be moving, and that the further you move from the nucleus, the higher the energy levels. So in other words, the more energy that's stored in those levels. This is kind of what he envisioned with the nucleus and then the electrons moving around in their orbits. We have our orbits here kind of laid out in our circles, our concentric circles. N equals 1, that would be the first energy level. N equals 2, second, third, fourth, and so on. Some definitions. We have quantum. It's the amount of energy needed to move an electron from the energy level that it's at to the next higher one. And quantum leap? No, it's not just a sci-fi term. It's also an abrupt change in energy levels. And remember, this is in reference to the electrons. And energy levels are also not evenly spaced. So you couldn't measure and say, okay, each one is half a nanometer spaced apart. They weren't equal. It's just another diagram. We talked about this on Tuesday, how if an electron drops energy levels and gets closer to the nucleus, it emits photons, which is making it an exothermic process. It's giving off energy. And if an electron absorbs a photon or absorbs energy, it can be promoted to another energy level, and that would be an endothermic process. Our quantum mechanical model, it was derived from mathematical equations from Mr. Schrödinger. Some of you may have heard about Schrödinger's cat. It does have to do with electrons in the unseen. Maybe I'll find that joke for you later, or that story. The differences are that electrons are still confined to quanta or levels, but it doesn't define the exact path. So now we're looking at probability. The quantum mechanical model, it estimates the probability of finding an electron in a certain position at a certain time. So we're just looking at probability. And because it's a probability of where we'll find the highest chances of seeing an electron, we get kind of this fuzzy representation. And once again, this is where you would expect to find the electron 90% of the time. So the darker the area, the higher likelihood you'd find it there 90% of the time. So this is where we have the highest likelihood. And then you see we have this kind of slightly emptier space where we have a lot less chance, according to this, of finding an electron. And then we have another band that's slightly darker. When we look at atomic orbitals for the quantum mechanical model, we have principal quantum numbers, which are designated with an N, and these are associated with the energy levels. So N equals 1 is the energy level closest to the nucleus, so the most inner circle. Principal quantum numbers also are divided into sublevels, and they're equal in number to the principal energy levels. So level 1 has one sublevel. Level 2 has two sublevels. Level 3 would have 3. Level 4 would have 4. And you see, it's kind of like having a house or a building. We have a one-story house here, so one house with one floor. Our second shell we could think of as a two-story house. It's one energy level with two subshells, so two floors. And here we have a one house, once again, because it's one, actual level, but that house has three floors within that one house. And we'll look at a little closer to see if we can explain it even better. So the shapes of the electron clouds in the quantum mechanical model of the atom are all different. Our s orbitals are like a sphere, and they hold two electrons. And we already knew this from previous units, but now we're going to look a little closer. The p orbitals are shaped like a dumbbell, and they hold 6 electrons total in the p orbitals. D is a complex shape, and it holds 10 electrons, and F is also a complex shape, and it holds up to 14. So here is the illustration of what they look like. So here for n equals 1, so this is the s orbital when n equals 1, when the level is the first level. It's just a sphere. The s orbitals for when n equals 2, you have two essentially rings or spheres inside each other. N equals 3, you're going to have 3 spheres, 4, and so forth. Here is what the p orbitals look like. So this is the dumbbell shape. This is the d orbitals. They're getting more complex. And then we have f orbitals down here. So when n equals 1, and that's the energy level we're at, it has a 1s sublevel. So only the sphere. When n equals 2, it has a 2s and 2p sublevel. When n equals 3, you have a 3s, a 3p, and a 3d. When it equals 4, we have 4s, 4p, 4d, and 4f. And we're going to look at how these are ordered. So energy level 1 can hold 2 electrons max. And we already knew this. The first 2 columns in the periodic table, they hold up to 2 electrons. They're the s, essentially s block. When n equals 2, can hold 8 electrons max. So this is going to be, I don't want that. When n equals 2, we have 8 electrons max. So that's going to be, sorry about that, 2s and 2p. And this can hold 2, and this can hold 6. Remember, when we look at the p block on the periodic table, they have 6 valence electron shell spaces, so to speak, and then the other 2 are made up from the s block, and that gives us a total of 8. Once we get into n equals 3, we're going to have our 3s, our 3p, and now we're going to throw in the d level. So we have 2, 6, and the d orbitals hold 10 electrons. So we can hold a max of 18. And I think you see where this is going. We have 4s, 4p, 4d, and now we're going to add the f orbitals. We get 2, 6, 10, and if we look back, we can see what we were holding in the f orbitals. 14 for the f orbitals. So we have 14, and that gives us our 32 electrons. So here we're going to fill in the information that's missing, which in this case is quite a bit. We're going to look at the energy levels. So we're going through all 7 that we know about. And remember, these are equivalent to the rows on the periodic table. So row number 1, remember that's just hydrogen and helium. The only orbital that that row has is an s orbital. Number of orbitals, s equals 1, so we have 1. And each orbital can only hold 2 electrons. Now for helium, we would have a total of 2 electrons. For energy level 2, now this is where we have lithium all the way over to, I believe, neon. I'm sure you'll correct me if I'm wrong. Now, lithium is in the s block, so we have s orbitals, and we know that we also have p orbitals because we're now going into the p block over on the other side of the periodic table. S has 1 orbital, p always has 3, for a total of 4 possible orbitals. Each orbital can hold 2 electrons. So we're going to multiply this by 2, and that's going to give us 8. We add this up, we get 10 electrons now. So if we have full 1 and 2 energy levels, we'll have a total of 10 electrons. 3 is going to have S, P, and now D. S equals 1 orbital. Sorry. Totally got off there on where I was writing stuff. So here, S, P, and D orbitals. S equals 1, P equals 3, and D equals 5. So we add that up for a total of 9 orbitals. And 9 times 2, because each orbital can hold 2 electrons, gives us 18 for a running total of 28 electrons. 4 has S, P, D, and F orbitals. We get S equals 1, P has 3 orbitals, D has 5, and F has 7, for a total of 16. 16 times 2 electrons each gives us 32. Add that to our running total, and we get 60 electrons possible in our 4th energy level if it was totally full. When we get to 5, 6, and 7, things get a little more interesting. We have S, P, D, F. Now we're going to throw in a G level. S equals 1, P equals 3, D has 5 orbitals, F has 7. And now our G actually holds 9. When we total that up, we get 25 possible orbitals times 2 is 50. And now we can have up to 110 electrons if we were to have a number up to 110. So element 110 would have full energy levels up to the very full level 5. This is going to continue on. We're going to leave it there because this is the most we're going to be concerned about. And just know that this pattern continues through 6 and 7. So hopefully my rambling has given you plenty of time to fill this in. I'll move on. So there's a couple ways to do electron configuration. It has to do with the ways in which the electrons are arranged around the nuclei of atoms. And we have 3 things that determine how they're configured. We have the Aufbau principle, Pauli exclusion principle, and Hund's rule. The Aufbau principle is that electrons enter orbitals of lower energy first until all electrons have been accounted for, also known as the good mama rule, making sure all their little electron children don't go wandering off. So we're going to fill our lowest energy levels first. We're going to fill up the 1s and then fill up the 2s, the 2p, 3s, and so forth. We can't just go, okay, I'm going to put my 3 electrons for lithium. I'm going to put 1 in the 1s orbital, and then I'm going to jump all the way to the 3d. It doesn't work that way. We have to fill them in order. The Pauli exclusion principle says that an atomic orbital may hold at most 2 electrons and spin in opposite directions. So this is where I was saying that S had 1 orbital, P had 3, D had 5, and F had 7. So the reason that I was multiplying by 2 is because each one of these can hold 2 electrons. So 3 orbitals can hold 6 electrons. 5 orbitals can hold 10 because we can have 2 in each orbital spinning in opposite directions. So for the S, I can have an electron here and an electron here. This one would be spinning this way, and this one could be spinning this way, or plus 1/2 spin, minus 1/2 spin. Our p orbitals, they look like the dumbbells. So we have 1 dumbbell here. So there'd be an electron spinning with a positive 1/2. And then a negative 1/2. That was 1 orbital. Then we'd have a second p orbital where the electrons would have opposite spins. And then I'm not a good 3D drawer, but something like that coming out the z-axis, much easier in 3D. You'd have the negative 1/2 spin and a positive 1/2 spin. So this would be the p orbital filled with 6 electrons, 2 each one. Then we have Hund's rule, and says that when electrons occupy orbitals of equal energy, 1 electron enters each orbital until all orbitals contain 1 electron with parallel spins. So the way we draw that, let's say this is the 2p orbital. Now if I have something with 3 electrons for the 2p orbital, I'm going to do this half arrow. That's 1 electron. I'm going to put in another one with the half arrow going the same direction, and then I'm going to put one more. So this is one orbital, one orbital, one orbital. I filled them all halfway with the same direction. So this would be equivalent to having a plus 1/2 spin electron in each of them. Now, if I had one with 5 2p electrons, I'm going to start back over here, and now I'm going to fill in 2 more, putting 1 in each one. So this is now full, and this one is full, and we could have one more. And this is kind of the principle behind bonding. Now when we wrap all this together, we can do our valence electron configuration. So hydrogen has 1 electron. Remember, the number of protons equal the number of electrons, and the number of protons equals the atomic number. Our 1s orbital, so that can hold 2 electrons total, but I only have 1. So it's just going to have this half arrow and nothing else. My electron configuration, I have 1s, so right here, that tells me 1s, 1. Now this isn't a power. This is telling you how many electrons are in that shell. So 1s1 is the electron configuration for hydrogen. Helium has 2, so we're going to fill up our 1s, and now it's full. We've used up our 2 electrons, and we're good. So we have 1s, and once again we go back here, and now we have 2 electrons in there. Lithium has 3 electrons, so we're going to fill up our first energy level. Now I have 1 more, so I'm going to add it to my 2s. And that's all I have. I've used them all up. So I have 1s2, so 1s, 2, 2s, 1. So 2s, and I have 1 electron. Carbon has 6. So I'm going to fill up my 1s and my 2s. And now, how many can 2p hold? I'll just imagine you're all saying 6. So it can hold up to 6. Well, if I've already used 4, I only have 2 more. So they all have to start the same direction. And we can even draw our lines to represent the 3 orbitals if you need that visual. So now I've used my last 2 for a total of 6. So my electron configuration, I start back at the basics. Got 1s2, 2s2. Now I have 2p, and I have 2 electrons in that shell. So that's the electron configuration for carbon. Nitrogen has 7, so it's going to start off looking just like our carbon. And draw my 3p orbitals, and now I'm going to fill them all up, and that totals my 7 electrons. So 1s2, 2s2, 2p3 now. Oxygen has 8. Fill up this one, my 3 levels. So I'm going to fill them up with the electrons going the same directions. So that's 7. Now I start back here and add 1 more. And I start pairing them. So that's my 8. I have 1s2, 2s2, 2p4. Fluorine is 9. So I'm going to have the same as the oxygen before it. Pair them, or single, 1, 2, 3, 4, and 5. So I have 5, 6, 7, 8, 9. And I come over here and I start from the beginning. Neon is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And hey, look, we have 6 here. 6 is the most it can hold. And then if we look at all of our level 2 ones and add them, we get a total of 8 electrons. And conveniently, neon has 8 electrons in its valence shell because it's a noble gas. So it worked out well. 1s2, 2s2, 2p6. This is noble gas configuration for neon. And sodium, we'll do one more. We have 11. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now, since we still have more, we have to go up to the next level and start back at our 3s. So there's our extra one. And that gives us 1s2, 2s2, 2p6, 3s1. Hopefully, after all of that, you're kind of getting the idea. Electron dot diagrams, we call these Lewis dot diagrams. You probably did these in 8th grade, I think. And it shows just the valence electrons, and it shows how they fill in and arrange themselves around an atom. Alright, so when we draw these, we're going to just look at the valence electrons, and we're going to do the dots around the chemical symbol. Now in this case, this is kind of a guide for any of the elements in family 1A, for example, who are all going to have the valence electron configuration of some level, so 1, 2, 3, 4, etc., and then S1. So I'm just going to use X as our generic symbol, and then I have my 1 electron. So it can bond once, and we know that our common ion charge for the alkali metals is +1. For 2A, which are alkali earth metals, we're going to have 2 valence electrons, and we're always going to pair for just an elements Lewis dot diagram. Now we're not talking about bonding, but just the unbonded element Lewis dot diagram. We're going to pair our S level electrons together. And this shows that it's full. It's filled that level. It doesn't want to bond, but it will get rid of both of those electrons if it can. Now for those in column 3A, that would be like boron. Our X, we're going to take our 2 electrons and pair them up to represent our S2. And then we have one more, and we're going to put that on the next area. And we can imagine that this is like a box around our chemical symbol. So on this side we add 2, then we're going to do 1. And these like to give up all 3 electrons still. Now those in 4A, they have 4 valence electrons, 2 plus 2. Have my X. I'm going to pair those to S, and then I'm going to singularly put those 2 remaining electrons. So it can bond twice. we'd have one here and one here. And these are plus or minus 4. Depends on what it's trying to do with its valence electrons. For column 5, we have 5 valence electrons. I'm going to do X, fill in my S, 1, 2, 3. That gives me a total of 5 electrons. So it could bond 3 times. You could have another bond here, here, and here. And that likes to take 3 electrons. For our column 6, we're going to have our 2s electrons, and then 1, 2, 3. And since I can only have 2, each side represents the orbital, I now have to start filling in again and pairing them up. So now I have 2 that are full and 2 that still have room to pair up. And this is oxygen, and those in the same column, they want to take 2. When we have NS2 NP5 for the valence configuration, we're going to fill that s orbital. 1, 2, 3, 4, 5. It wants to make up to 1 bond there, and it can take 1 electron. S2 NS6, this would be like our neon. We're going to fill in the S. 1, 2, 3, 4, 5, 6. This has 8. That's our octet. It's stable. It doesn't want to bond with anything. It doesn't have any charge. And these are our noble gases. So hopefully this is coming back to you. Quantum numbers. We have principal quantum number that refers to the energy level in an atom. So that symbol is N. And it can have a whole number value from 1 to 7. So we're going to think of this as the floor in the hotel. So what floor number is that electron on? Now our secondary quantum number refers to the type of orbital. This has a symbol of L. This is actually an L. Usually you see it written kind of as a cursive L. And what we're doing is we're essentially giving each electron an address, its own unique address. So our secondary quantum number tells you what kind of orbital. So we have S is 0, P is 1, D is 2, and F is 3. So we're thinking of this as the room number in the hotel. Our magnetic quantum number refers to which bed the electron is in that hotel room on that floor. It has a symbol of M sub L, so you may see it more looking like that. An S orbital can only have a 0 as the number. P orbital can either be -1, 0, or 1. D can be -2, -1, 0, 1, or 2. Remember, D orbitals, they have 5 orbitals. And so this makes sense that we have 5 locations. And F has 7, so we go from -3 to 3. And our last number is our spin quantum number. It tells you what direction the electron would be spinning. Remember, we can only have 2 electrons in each orbital. One has to have a +1/2 and one has to have a -1/2. The symbol for this quantum number is MS, and it's either a +1/2 or a -1/2. So that's the direction you face in the bed. So let's say when you lay down in the bed, here's your nice hotel, bed stands and pillow. Do you face this lamp and the lovely curtains to your view of another building? Or do you face this way and have a nice view of the door? That looks like we're about through. Now I just want to give you an example real quick of what you could do with those numbers. So if I asked for quantum numbers of, let's say, lithium, so I have lithium's has 3 electrons. Its configuration is 1s2 because it's filled both 1s orbitals, and I have 1 left over, so that's going to be now in my 2s orbital. And let's take a look at where this electron is going to be located. So we have a principal quantum number that is going to be level 2. So it's going to be 2. The type of orbital it is, that would be our second quantum number. An s orbital has a value of 0. Our magnetic quantum number for the s orbital is also 0. And now, since I only have 1 electron, I can have it have a positive spin. So this equals the address of the 1 valence electron for lithium. So you'll definitely want to keep these handy for the worksheet you're going to work on because you'll be writing electron addresses very soon. So hopefully you're all still awake. Once again, I apologize profusely to my guest teacher who has potentially seen this 3 times now. You can go look at this on YouTube tonight if you need to get some stuff if I went through too fast, and it should be there for your reference. Otherwise, I look forward to seeing you tomorrow. I hope you have a great rest of your day, and good luck on the homework, which you should be assigned in just a minute. Have a good day. Bye.